C++ is a language that allows us to program in many different styles. Technically, that's called a multi-paradigm programming language. And we've been using it to program just with functions and so on. But a very important aspect of C++ is the fact that it's an object-oriented programming language. And what that means is it lets you program using an object-oriented style. So we're going to start with some examples, and I'm going to go explain this in much more detail and see how we can build our own objects and programming with those. So first of all, let's take a look at an example. Let's say I want to work with fractions, as rational numbers. I want to be able to say, you know what, I have a fraction, and my fraction x is going to be, let's say, 1/2, right? Then I have another fraction, let's say y, and y is going to be, say, 2/3. So how do I do this in C++? How do I work with fractions directly in C++, right? So I know that 1/2 is really 0.5, and 2/3, what is that? That's 0.666, all the way out there. But I don't want to do that. I want to do, when I do it with this, if I say 2/3 is 0.666, I don't get a very precise answer. I want to be able to deal with the fractions themselves and do the arithmetic with the fractions. So the question is, how do I do that in C++? I know that in C++ I can work with an integer, right? I have an integer data type. I know that I have a double, right, data type. I have a char data type. But do I have a data type that's a fractional data type, right? Do I have a way? And the answer is, unfortunately, not. So I want to be able to write programs that sort of look like this, right? I want to say, look, I have a number x, and number x, I want x to be, I have a variable x, I want x to represent the fraction 1/2. So maybe I can use something like this. I can say I have a new data type. Data type is called a rat for rational number, and x is the rational number. And I'm initializing x with 1/2, and I write that as 1/2, right? Likewise, y is also a rational number. All these things are rational numbers. And then y is 2/3, right? And then z is going to be a rational number. I'm not initializing with anything. And what I want to be able to do is I want to do, say, arithmetic on rational numbers. I want to say z is equal to x plus y. I want to be able to output my rational numbers. Once I set x to be, what was x set to be? Y was set to be 2/3. I want to be able to change, say, set the numerator to 7, right? So it's going to be 7/3. I want to be able to set the denominator to 2, right? And then I want to add them again, or I want to multiply them, or I want to subtract them, right? I want to be able to read them. I want to be able to write them. I want to be able to have them interact with my built-in types. So to be able to say 3, which is an integer, times x, plus y times 5, and then take the whole thing and add it to a 10, and output the result. Put it into z and output the result. The question is, I want to be able to do this, but directly in C++, I can't, because C++ does not support directly a rational data type, right? So, but you want to do that. What are you going to do? How are you going to do that? And so the answer is, one of the things we get in C++ is C++ lets us build our own data types, right? And if we build a data type and we teach C++ how to do this, we can then do what we saw in the previous page. And we do this by creating a class to represent a new data type. And then once we have the class, then we can declare variables to be of that task. So for example, if I say, if I somehow create a new class, a new data type called rational, rat, right? And I somehow tell C++ what that means, I can then say, with respect to the question of why this is called object-oriented, there's a lot to be said about this, but for now, we'll just suffice to say that what we can do now is by defining a new class, a new data type, we can create objects of that data type. By that we mean something like if you have a data type to an integer, the int data type, so there are elements of that data type, 3, 4, 5, we can call those the objects of that data type. So we create, by making a class, we'll be able to then stamp out various objects of that class, and we will program directly with those objects. So in terms of the define, once we tell C++ what we mean by a rational number, then we'll be able to create those objects and program directly in terms of those objects. Okay, so let's get technical here a little bit and talk about what we mean in general by a data type, because what we're saying is that the class will let us create new data types. So what, for example, makes an int an int? Right? So for example, if I say that I have, let's say I have an integer I and I have an integer j, right? So what does it mean that it's I and j? What can I do with an I and j? So first of all, I can add I and j, right? I can subtract I from j. I can multiply I and j, right? I can take I and say odd mod 3, for example. I can use the mod operation and so on, right? So an integer data type, or any data type, gives me basically, number one, it gives me a set of things, right? A set of some kind of, call them things or objects, right? And certain things belong to that set. So for example, if I'm talking about an integer, 1 is an integer, 15 is an integer, -7 is an integer. But 3.9 is not an integer. That is not an integer, right? So first of all, the first thing is it's a set of things. And second of all, what makes a data type is the kind of operations I can do on those things. So we saw I can add, subtract, multiply, divide, and so on, right? So not only a set of objects, a set of things that constitute the elements in that data type, but also the operations that I can do on elements of that data type, right? So for example, what about float, right? If I have a floating point data type, so I can say x and y are floats, right? What can I do with them? I can say x plus y minus y times y. But can I say, for example, x mod 3 if it's a floating point number? So the answer is no, right? So a floating point also, number one, gives me a set of things and a set of operations, but the operations I can do on integers are not the same of the operations I can do on floats, right? So the data type is basically those two things together, right? A set of things and a set of operations that I can work on those things. I can apply to those things. Now, what the class what the class mechanism in C++ gives us, it gives us a syntactic framework, gives us a way for describing to the compiler the two things that make a new data type. In other words, number one, I want to be able to describe what kinds of things are in this class. So if I'm defining a class of rational numbers, I have to tell what is a rational number. Now, integers, right, and floats, that comes prepackaged in C++. It's part of the base language. So the C++ compiler knows what an integer is. It knows how to represent the integer internally, knows what it looks like, right? And then basically, once it has the internal representation, when I say add two integers, it knows exactly what that means, right? But if I want to create a new data type like a rat, I have to teach that to C++. When it's going to make me the set of rats, I have to tell it what a rat looks like. So number one, I have to tell it the representation of when I tell you that X is a rat, what's it going to look like internally? How are you going to represent it? And then the second thing, when we make the interface, these are sort of the operations, right? The operations that a rat can answer to. In other words, if X and Y are rats, I want to say X plus Y, X minus Y, X times Y, X divided by Y, and so on, just like my other data types, right? So that's the idea. So the class idea, and when I have in C++ and in the other languages too, it lets us make new things in language, new data types, new things that I can operate on directly, right? So if I have an integer, I can operate on that because that's part of the basic language. But if I want to deal with rational numbers, that's not part of the language. It lets me extend the language to add new kind of data types. Just an aside, all programming languages, as they grew, you can look at a graph like this, right? So for example, in a data type, in some language, I can say that I have nouns, right? And I have verbs. And the richness of the language depends on how many nouns and verbs I have, right? I can say I have a language that has a lot of verbs, but not too many nouns. A language that has a lot of nouns, not too many verbs. A language that has both nouns and verbs, and so on. That's natural languages. Programming languages also. In programming languages, I can say, what are the nouns? Those are the basic objects in a data type. So in C++, I have integers, I have floats, I have chars, I have bools, and so on. And what are the verbs? So the verbs are the operations that I can do on those languages, right? So this is true for programming languages as well. And languages, natural languages, grow. So for example, 20 years ago, there was no verb to Google, right? Now there's a verb to Google, right? So languages grow, programming languages grow as well. So even from the very beginning, there was an ability, you started with a certain base set of nouns, and a basic set of verbs, and the language allowed you to create new verbs, and those were called functions, right? So if I wanted to, let's say, sort something, so this sort was not built into the language, let's say, but I can add that word sort, I can add that verb, right? And now I've extended the language even more. But originally, the languages did not let me create new nouns, right? So with the object-oriented syntax, with this ability to create new classes, I can make the language not only grow in terms of verbs, but in terms of nouns also. And by making new classes, the nouns, every time I introduce a new class, like a rational number, I'm also going to have new nouns that can work on those new verbs, new operations that will work on my classes. So it's an ability to, number one, build a language. And why is it important? Why would you want to do this, right? That's an important thing to think about, because if I want to deal with fractions, I could get away without that. I could say, I could create two. I could say, listen, I have an integer called n for the numerator and one called d for the denominator. And then when I deal with some particular fraction, I'll make sure, I set n to be the numerator, d the denominator, and then maybe build a function to work on these things. But I'm really working very low down, right? It's sort of a primitive way of doing this, because when I think about it conceptually, I think about this as a unit, right? I think, well, I have some rational number that has a numerator and a denominator. Wouldn't it be much better to be able to say, listen, I have some n over d, right? Some x, which represents the numerator and denominator, and it represents a fraction to me, and then I can add it to another fraction, right? I think on a much higher level. And when I do that, solving the problem is much easier. What I do is, right, I can now create a little space in my world, my programming world, where by creating these new objects, I can describe the processes in terms of those new objects, right? And so that takes it up to a higher level and makes it easier to describe my algorithms, because the algorithms are now described in terms of these objects that make sense for them, right? Imagine a game program, right? Let's say a chess program. If you can actually create pieces like knights and kings and pawns and so on, if you can describe your algorithms in terms of what these objects give them actions that they can do, then when you write your program in terms of those objects and the actions, whoever's reading the program, it's much clearer to them. And you're writing the program, since you're writing in terms of the objects themselves that define the game, it's much easier to think about and it's much easier to write. So that's the basic idea, right? I want to make new data types that reflect the problem domain that I'm trying to solve. So for object-oriented programming or object-based programming, I'll address the distinction in a little while. But what are we trying to do? We're trying to create these new data types. So to create the new data type, right, we said what has to be done over here. Number one, you have to essentially give a definition to the compiler. So the compiler knows when you say that I have a rat, here's what a rat looks like internally, so you can create it internally, and then here's what it could do. We have to be able to describe both of those things. So the class mechanism basically looks like this. It's a syntactic way of putting everything together. So you say like this, you say, I have a class, right? In other words, what tells the compiler is I'm introducing a new data type over here, right? I have this class, and then you say the name of the class, right? So the class, let's say, that we're going to look at is called a rat. And then you open it with some brace, and then at the bottom, you close it with some brace also, right? So this is the basic mechanism, say, and within here, I'm going to define my class. So this is a first attempt at this, but this will give you a high enough picture of what's going on here, right? So I'm defining a class called rat. Now remember, what are the two things that I need to be able to say? I needed to say, what does it look like, right? What does it look like? What does it look like? Means when you create one of these things internally, what's the representation in the memory, right? What is it? What is a rat? How am I gonna describe a rat in the memory itself, so that I start to manipulate it? And then the second part that you need to do is you need to say to the compiler, what can I do with it? What can it do, right? So this is the representation, right? And these are the operations, right? And those are the two things that you need to say to the compiler. Just if I have a data type of an int, so the compiler already knows the answer of how the representation is. It's usually two's complement numbers. We saw that in class. And then, so that's the first thing. The compiler knows that already. And then the compiler says, well, what can it do? And it knows. It adds, subtracts, multiplies, divides, and so on. So when I make my new data type, I have to have some way of defining this to the compiler. And I say, that's the way I do it. I say, listen, I have a class, and that's the syntax. It was all lowercase, CLASS, a new class, which means a new data type. I give the name any way that I want. There's nothing, the compiler doesn't know when I say rat that I mean rational numbers, right? But I call the thing a rat. And then over here, somehow I tell it what it looks like. When I create a rat, this is what it's supposed to look like. And then I say, what can it do, right? So this is the basic idea. And this is the idea of encapsulation. I'm using the term a little bit non-standard, but basically, why do we call this encapsulation? Why is this called encapsulation? Well, here's a capsule, right? Here's a medicine capsule. So what happens with a capsule? Well, you have a bunch of medicine in here, right? There's all this medicine, but you don't get a hold of these little pieces. You don't get a hold of that. What you do is they take this package and they put all the medicine inside the package. You get the package itself and you swallow it whole, right? That's the idea. I take a bunch of disparate things and I put them together and I treat it as one unit. So in C++, I am encapsulating, I'm taking everything, both the representation and the operations, and I'm encapsulating them, I'm putting them in one syntactic unit. I say the word class, I say rat, I open it with a brace, I close it with a brace, and included in all that, just like you saw in the medicine, everything is included in here. So if I want to know what can this thing do, I just look in the part of the syntactic representation, and I look, that's what it can do. Those are the operations. And I say, what does it look like internally? I just look at this, and it tells me what the representation is internally. Okay, so what is data hiding? What does that mean? Well, data hiding means you can't get a hold of the insides of the data type, right? Just like if somebody takes that medicine in a capsule, they're not supposed to break it open and look inside, right? There's certain things the doctor tells them to do. Take this, with 2 cups of water, right? And so they're supposed to use it as one unit. They're not supposed to open it up and break it inside. And so the C++ class mechanism gives me a way of saying that you can use my rat, you can do all the operations that a rat can do, but I want to make sure you don't get inside there. And the way that it does it is it says, I'm going to say what follows over here is going to be private. We're going to get into this in more detail later on, right? When I say this is private, it means that it does not let you get inside there. And this is very, very important. The idea of allowing, of providing a way, a mechanism for the programmer to say that the user of his class, this new rat, for example, you only have to use it by applying these operations. Don't get clever and go inside, right? The same thing when I have an integer data type. So I might know how it's represented internally, but I'm encouraged as a programmer not to use my knowledge of that representation. I'm encouraged I'm just told to use the operation. I want to add, let's say I want to do the following thing. Let's say I is an integer, and I give I a value of 1, right? And then I want to multiply it by 2. I want to say I is equal to I times 2, right? So this is how I do it. I say it's I times 2. But now, there's another way to do this, right? Because I know the way it's represented. So watch the following. So here's a simple C++ program, right? I have an integer I set to 1, and I see out I and then 1. So what's going to be printed? What's the output of this program? So let me compile this and run this and see what happens. So I would expect what? 1, 1, right? Now, why do I get 1, 1? Because I is 1, right? And it prints I, and it prints 1. So I get 1, 1. No surprises, right? Let's just come here and change it a little bit. I just put some parentheses in here for a second. And I say, I want you to print it out, but I'm just parenthesizing it now. Okay, so what's it going to print now, right? I would assume the same thing, right? It's going to print, because I'm saying I want you to print I, and then I want you to print 1, right? So if you want to really be surprised over here, just copy this program and run it, before you watch the video. Just stop the video. Very simple program. Put into the compiler and run it. Okay, let's see. Let's compile this and run this. And what happens, I expect like I'm printing a 1 and another 1. It should be the same as the previous one. I should get those two values. What does it say? Huh? A 2. Why does it print a 2? Why does it print a 2? And so the answer happens to be very interesting. When we say cout I and I say 1, the real question is, what does this operation really mean? Right? Well, you learned in 111 what it means. We've been using it all semester. It means output, right? But in fact, what happens is this is an example of an operator that is overloaded. We're going to see a lot of this in a little bit. Overloaded. And what that means in C++ and in many programming languages, that the same operation means different things in different contexts. So in this case, cout is an example of an object of a certain class, and it's the OStream class. We'll talk about that later too. And what this means is, and it's an object, it's like an integer, but it's an object of that OStream class. And this says to the cout object, which as far as we're concerned can mean to the screen, right? To the cout object, to the screen, I want you to put, this is the verb here, I want you to put whatever this thing is here. So in this context, right, the two left shift operators, the less than operators means put, output it. But in this context, if I don't have the parentheses, if I simply had what we saw before, right, the first thing I wrote cout, right, and then I want you to print I, and then I want you to output 1. So then what happens is first prints an I and that 1, so we got a 1 1. But once I do this, then I say, well, I want you to figure this out before you print it out. So what the compiler says is, what is this thing over here? What is this? Well, I is an integer, right? And with respect over here, when it looks at this, it says I is an operation that I'm doing on the cout object. But once I put the parentheses over here, right, these parentheses, so it says I'm going to apply this parentheses to the integer over here, right? So what I'm doing to the integer is this, right? This. What does that mean, right? This is not an object. This is not the output object, the cout object. What does it mean? So the base, this is the actual base meaning of the left shift operator. We call them left shift. These two less than is really called left shift. What it means is take the integer over here, I. Now, what is the value of this integer here? What is the value? Well, it's a binary number 0, right? It's represented as a 2's complement number, 0, 0, 0, 0, 0, 0, 1, right? That's what it looks like internally. It's a binary number. And what this means when it operates on integers is left shift. Take all the bits, right? Takes all the bits, and I want you to left shift them, move them to the left. How many bits to the left? Well, I want you to move it 1 bit to the left. And so what's going to happen is everything's going to shift this way. I'm going to get a 0, 0, 0, dot, 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 0, 0, 1, and then fill it in with another 0. After you shift it in, put a 0 over here, and you're left with this binary number. What is the binary number 10? The binary number 10 is 2. That's why it prints a 2, right? So now you could actually multiply by 2 in one of two ways. The way we originally saw, if I has a number and I want to multiply by 2, I can do it like this, right? And when I do it like this, I make no assumptions whatsoever about the internal representation of this integer I, right? But if I want to be clever about it, I say, I'm a smart guy. I know what this really means, right? And if I put this operator on an integer, right? If I say I and then I say 1, I know this is the left shift operator when working on an integer, and that's going to move it over by 1 and add a 0. Well, that's the same thing as multiplying by 2. So here what I've done is I've used the internal representation. I didn't use the data hiding of it. I went into the internal representation and I started manipulating the bits because I knew how it represented, right? And so I shifted by 1 and it gave me a 2. So which should I use? So the answer is you say I times 2. First of all, because when somebody reads this, they know exactly what that means. But secondly, let's say somebody comes along and they say, you know what, I'm writing a compiler, right? But I have a completely different way. There's another completely new technology, and I'm representing my integers differently. You're going to get the same outputs. It's going to function equivalently to the way it does if I would represent these things in binary, but I have an absolutely another representation. So if you say I times 2, right, it'll get you to give you the right answer. But if you start shifting bits, it won't work anymore. So there's a basic idea here, and that is, do not write to, when you write programs, use this and don't use this. How do we say this? How do we say this as programmers? What we say is write to the interface, not to the implementation. Right? What does that mean? It means the interface is do this right over here, right? Use the kind of operations the data type provides for you. Multiplying, dividing, adding. Don't write to your knowledge of the representation, because first of all, it's clear. That's why we made these operations, so they tell you exactly what they're doing. And likewise, and besides which, if you write to the representation, right? If you knew, for example, that this means take I and left shift it by 1 bit, what happens if I change the way I represent these integers? All your programs break, right? But I guarantee that the interface won't change. If I say I times 2, that's always going to work, right? So that's a very important principle of software development. When you have a class, don't try to get clever and get inside the representation. Write to the interface, not to the representation. So where we are right now is we know how to define a class. You know, on some very high level, you define a class by saying the word class, by putting these braces, and by defining what the representation looks like and the operations. So by encapsulation, we mean this, right? This and this, right? Putting everything together. And by data hiding, we mean some mechanism whereby you can say that my representation is inaccessible, it's private, it's inaccessible to the user, right? If they want to use my RAD objects, they have to do it only through the operations that I provide. They cannot do it. They can't get inside my object because I'm declaring it private, and the compiler will enforce that. Any attempt to do anything on the inside will result in a compiler error. So before we move on to consider the detailed implementation of our RAD class, I want to just make sure I want to define some terms here. So we've been talking about object-oriented programming and object-based programming, and we haven't really distinguished between them. So let's just do that, and then we'll go on. So what do we mean by object-based programming, and what do we mean by object-oriented programming? So what we've been doing here until now, defining a new data type, is this object-based programming. That means you basically declare a new data type by defining a class, and you use that as if it were a built-in data type. So when you have this object-based programming, you have the following things that we saw. First of all, you can do data hiding. That's number one, data hiding. And number two, you can do encapsulation. And we just spoke about those things. When you add to these, so this is data based programming, right? This is object-based programming. If I add two other things, if I add two other things to this, right? If I make a bigger thing, add two more things, I'm going to get object-oriented programming. So what are the two things I add? And one is called inheritance, and the other one's called polymorphism. So I'm not going to go into details of that here. Once you take the 2.12 class and you do Java, Java starts with that from the very beginning, because Java is a pure object-oriented programming paradigm. As I said at the beginning of this video, in C++ is a multi-paradigm language. I could use this completely without objects. It's not possible in Java. Java, everything's an object. Not so in C++, right? You've been programming the whole semester without even knowing that there's a thing called an object or object-oriented programming. So when you have an object-oriented program, you're using both data hiding and encapsulation, and together with that, you can use inheritance and polymorphism. What does inheritance mean? Inheritance means I can basically create a hierarchy of classes. So for example, I could say something like, here's a person, right? Here's a person. And a person has certain characteristics, right? So for example, a person might have a name, right? And a person might have an address, right? You know, various characteristics that I would characterize the person with, right? An address and so on. So so I can make an object, I can make a class called person, and then do various things. But you know, there are certain kinds of people that have additional things. So for example, I might have a student, right? A student. Now a student, of course, is a person, right? So here's a student, and a student is a person, but a student, in other words, a student has all the same attributes that a person has, namely a name and an address and so on. But a student has different attributes as well. So for example, a student might have a school that he attends, right? It might have the year in school and so on. It might have a major, right? So that would be a student. But now there could be different kinds of students, right? For example, I can have an undergrad student, right? An undergrad student might have various characteristics that extends the idea of a student. I might have a graduate student, right? A graduate student might have an advisor. I might have a PhD student, right? And so what happens, I get this class hierarchy, right? Where everything on the lower classes are specializations of things on the upper classes. So for example, when I define a student, I don't have to say that the student has a name or an address, because since a student's a person and a person has those things, so a student has those things as well, right? And an undergraduate student has everything that a student has plus whatever additional things that the undergraduate has. A graduate student has the same things a student has except some additional things the graduate student. And a PhD student might have a thesis topic and a lab that they're associated with and so on, right? So that's what I mean by inheritance. The classes that are under the lower class in the hierarchy, called derived classes, so they are examples of things. They're instances of the classes on top, and they inherit the various properties, right? So a student would inherit the name, would inherit the fact that he has a name and an address, and an undergraduate would inherit everything that a person has plus everything that a student has, and so on. So that's what I mean by inheritance. What do I mean by polymorphism? Well, polymorphism means many shapes. And with that, in the context of programming, what that means is basically I can write programs. I could treat students as if they were people. Of course, students are people, but basically what happens is I can define functions that every person might have, right? And then when I want the student, now a student in this example here inherits from a person, but a student is not a person, in the sense that this is a special class. It's one kind of class. This is another class. It has all the characteristics of a person, but it's a different kind of class. A student object is a different object than a person class. But when I have polymorphism, I can actually call whatever functions, whatever operations are defined for a person, I can call them on students if I do certain things. And I don't want to get into details here because that's going to confuse the thing completely. But basically, when you add the additional things of inheritance and polymorphism, you get this full object-oriented programming approach. So when you're doing object-oriented programming, you have the ability to do data hiding, you have the ability to do encapsulation, but in addition, you can make these trees, these inheritance hierarchies, and then you can program the objects lower down in the hierarchy as if they were persons. Now, if that helps, fine. At this point, all you should need to do is get a feel for how this thing works. And as soon as you take the 212, as soon as you start, the Java, within a few weeks, this will be straightforward. Okay, but in C++, of course, you can do this. And so I just wanted you to see this before we move on to the actual example of the rat class. The rat class, we're only going to do these two things. We're going to define it. We're going to define a class, describe what the data is, and we're going to hide it so that the user can't get at it. And we're going to define its data, the operations it can do, and we're going to encapsulate them all. And then we're going to be able to say something like, I have a rat, and my rat name is, maybe see, Mickey, Mickey Rat or something, and my Mickey Rat is 1/2. Anything like that, right? So there's no inheritance over here. There's no polymorphism. But what I've done is I've extended the by defining this, by defining a class, and essentially telling C++ compiler what that class looks like, what the objects are made of, and what they can do. I have now extended the language so I can create new nouns, right? Mickey is a new noun, and what type of noun is it? It's a rat noun, right? It's an example of a rat, right? So the rat is a new class of nouns. So we're going to stop here, and in the next video, we'll go through the details of the implementation of the rat class.